solution to this equation with at least one of the CI's not equal to 0. That's the important bit, that one of these CI's is not 0. Assume it's V1. Why am I allowed to do that? Why am I allowed to assume that it's the first one?
Because you can switch like the order and go.
Absolutely. I didn't say which one of these vectors was V1. I'll just pick it to be whichever one had the coefficient that's not 0. Yeah, exactly. This ordering there's nothing special about the ordering. It's totally arbitrary. So let's pick the one where C1 is divisible, or C1 is not 0. So we can divide things by it. So if we rearrange all of this stuff, what do we get? We can subtract all of this over to the other side and divide by C1, and we get V1 is equal to negative C2 over C1 V2 minus C3 over C1 V3 minus C4 over C1 V4 minus dot minus CK over C1 VK. Does this make sense? What I did here in one quick step. I moved everything except V1 over to the other side. What did I get? I got that V1 is a linear combination of V2 up to VK. Which is what you were saying earlier. Well, you said it in slightly different language. Well, what's another way that I could say this? V1 is a linear combination of V2 up to VK.
It's a scalar of any other vector. Same
No, not quite. Not quite. So it's not a scalar multiple. It's quite possible, and this is where I should probably get to doing some actual concrete examples. That's not what a linear combination means. Somebody else want to say? Yeah. Yeah, it's in the span of these. So when these things, all of these C2 over C1, C3 over C1, all of these scalars could be something. So it's not just that it's a scalar multiple of the other things, but it's the sum of these scalar multiples. So we can put all these scalar multiples together and build this. We can really build this thing out of these other ones. Coming back to this picture right here, this V1 did not give us any additional information. It didn't tell us any. It didn't give us any vectors outside of V2, V4, V2, V3, V4 up to VK. All of the information about the span of these vectors, the vectors that we could get by linear combinations, would have been the same if we had left V1 out. If we had just thrown this one away. So there's a couple of ways to say this. V1 is in the span of V2 up to VK. That's one way to say it. I believe what you were saying earlier in the class. So, for example, 0 is always in the span of the rest of the vectors, right? Because we could do the same sort of thing. We could pick A1 to be non-zero. If we wanted to, we could subtract everything else over to the other side and divide by A1. And we would get 0 is equal to something over here. So we had that 0 is in the span of the other vectors. In general, these are linearly dependent if V1 is in the span. Maybe I should write all that out. V1 up to Vk is linearly dependent if and only if V1 is in the span of V2 up to Vk. Assuming that we did the proper reordering that we needed to. Okay, another way to say this. The span of V1 up to Vk is equal to the span of V2 up to Vk. Does that make sense? Including V1 into this set of vectors gives us the exact same span as if we left it out. So we could just throw that vector out and we would get the exact same span. I'll let everybody just sit with that for just a second. All right. Maybe it's some examples. Concrete. I'm intentionally straining you to think about these things in an abstract way.
So, as soon as, like, if you replace any one of those vectors, it doesn't, like, I'm thinking of, like, people trying to think of graphical representation of it, and I'm all in that part, I think we're going to talk about.
No.
So for 2D space, it's speculative, and if they all just kind of line up the line, I assume for 3D, if they're all heading the same plane, they're literally independent, they can all keep on defining just that same plane.
It depends.
But as soon as you have a vector that defines like something that's off that, then that means like there's a linear combination or like, yeah, like that, there's some linear combination that takes you off that linear.
Right, yeah. This is, well, what you're saying now depends on how many vectors we're talking about. So in three-dimensional space, if we just have one vector, then the span of that is just going to be a line, right? And if we have two vectors, there are two possibilities. Either they're on the same line, and so the span is still the same, adding that additional vector in didn't change anything. Or they're independent, and you get a plane. Okay? Now, when we got a third vector in, that third vector could either be on the initial line, which means it would be a multiple of the first, or it could be on the second line, which means it's a multiple of the second, or it could be anywhere in the plane other than those lines. Now that means it's not a multiple of the first one, and it's not a multiple of the second one, but it is some linear combination of the two. So it's somewhere in that plane. Now, if it's not on one of the lines, it's not on the plane at all, it's pointing in an independent direction, then this set is linearly independent, and what you now get is the entire plane, or the entire three-dimensional space. Okay? So three independent vectors in three-dimensional space. The span of that is the whole space. Right? The stereotypical independent vectors that we had in Calc 3, we call them I, J, and K. Right? One of them points this way, one of them points this way, and one of them points straight towards you. we're saying now is that we could have, we could have used any three independent vectors, because some linear combination of those three independent vectors would have given us any point anywhere in the three-dimensional space. And this is much closer to what we really mean by its three-dimensional space. It takes three vectors, three independent vectors, to define any spot. Now, just going a little further than what you were asking, will that answer your question first of all?
Yeah, that got pretty close to what I was trying to figure out.
Okay. One more vector. Let's say we have three independent vectors. They span the whole space. What happens if I throw in another vector?
Have to be a constant multiple of one of those other three, but still, if we're still talking about R three,
We're still talking about, yeah.
then if you have four, one of them has to be a combination of the three.
Yeah, exactly. Not a multiple.
Oh, that's what I'm saying.
It's very different, yeah. So it's, the linear combination is like an extension of the idea of a multiple. It's not really a multiple, but it's very similar. It's a very similar idea. In 2 dimensions, it is the same. Or in the case of 2 vectors, it is exactly the same. If it's a linear combination, then it is definitely a multiple. But when we go into higher numbers of vectors, then that's no longer the case. So if we throw in that additional vector in 3-dimensional space, we have 3 independent vectors, span the whole space. We throw in a fourth, that new one has to be in the span of the other ones, which means that this set of vectors is now linearly dependent. Exactly. Yeah.
So it's independent up until you pass like that R3 number, assuming that they're not just a scalar.
Yes. And maybe that's what we'll talk about now. So let's say V, we have a set V1 up to Vk, and the V are in Rn. Okay, if K is greater than N, so if there are more vectors than there are entries in the vector, then I'm going to call it V again. V is linearly dependent. And again, let's mark these things as special. Now an example. Oh, let's do a concrete example. So our first vector is 176. This is not exactly what's in the book, but it's pretty close. 176, 209, 315. So these are 3 vectors, three-dimensional vectors. Are they linearly independent? Just go with your gut. What does your gut say?
Yes.
I was about to say why, but you can't question your gut. You just know. I don't know, actually. Maybe these are linearly dependent. I honestly don't know. The example that it comes from in the book leads me to believe that they probably are linearly independent. But there's really only one way to find out. Well, there's actually a few ways. We didn't make this a theorem, but you know how to fill in the rest of it. If 0 is in the set of vectors, then that set of vectors is linearly dependent. So if one of these was 0, we would know immediately. That set's linearly dependent. If there were 4 of them, we would immediately know that it's linearly dependent. But there's only 3 of them, and so we don't have any of those special cases. And if there were only 2 of them, we would be able to say that they're linearly dependent if one was a multiple of the other. But we see that none of them is a multiple of the other. And so we can't take 2 of them to be linearly dependent. Maybe that's a good theorem. If V1 up to Vk is linearly dependent, this isn't in the book, but it can come straight out of your brain, right? Straight out of logic. If V1 up to Vk is linearly dependent, then V1 up to Vk, and then another one, Vk plus 1, is linearly dependent. You see why that might be true? I'm going to do a quick proof based just on the definition. So if this is linearly dependent, then we have A1, we'll reuse the C's, C1, V1, plus CK, VK is equal to 0, where at least one of these is non-zero. Who cares about the rest of them? We've got one of them that's non-zero, at least one. So, if I want to find a similar equation with these, I just throw that one in. C1, V1, plus CK, VK. I'll use the exact same C1, C2 up to CK that I used here. Did everybody read this? My handwriting is just bad. That's the problem. We use the same C's, the same scalars, right? And then that means that all of this is equal to 0. So now we just throw on some multiple of Vk plus 1. What multiple? The 0 multiple. And again, we get that it's equal to 0. So once it's linearly dependent, we can just grow this set as much as we want. Well, the span doesn't change. The span is still the same span. But they're linearly dependent. Oh, I said the span doesn't change. The span could actually change. We could pick a vector that is not in the span of these, but the set is still linearly dependent because you could have written these other ones in terms of each other. Wow, man, I'm trying, but I didn't even get to the example. Do some examples on your own. How about that? There's an idea. I wanted to kind of connect this thing with what we had talked about before with the row reduction. And you can see, not just from the, I didn't give a proof of this. That was totally geometric, you remember. And we only did it in 3 dimensions. Who's to say it doesn't work in 5 dimensions, right? What you can do is you can form the matrix. We go back to that equivalence. This is equivalent to AX equals 0. We're finding a non-trivial solution to AX equals 0. You do the row reduction algorithm on just the matrix A, and what you'll see is that you can possibly get pivots 1, 1, 1, 1 going in a diagonal line. But once you run out of dimensions, you see that that's the height of this thing, and you'll have well, some entries over here. You'll have free variables. And what that means is that those free variables give you non-trivial solutions, just like we talked about last time. So there will be non-trivial solutions in that case, which means if you have more vectors than you have entries, if you have k greater than n, then it has to be linearly dependent. That's the proof. That's the idea. Okay. Thank you. See you later.